Thank you, Alex, for the nice introduction. Hi, everyone. So I was hoping actually to be more informal for the seminar. So I didn't want to prepare many slides. So the idea, I hope that, so please interrupt me. I would be happy to have more interactions, more discussions during the talk. So what I would like to tell you is basically based on these works and some other works in progress with these people. And the idea was, what these works are about is basically hidden symmetries of gravity, which and an effective field theory approach to describe black hole perturbations. And this is what I will be telling you today. So I think I can skip all the introduction. In this audience, there is no need. Let me just say something that you all know. But again, in the spirit of being very informal, I don't want to give any introduction. We know that basically we have witnessed a revolution in astronomy after the direct detection of gravitational waves, and the number of events of observations are going to increase. So this is giving us a unique opportunity to test the general relativity, as we know, and shed light on the fundamental properties of gravity and black holes and astrophysical compact objects. And especially in light of envisioned third generation detectors, as we know, and also space-based detectors like these. So it's pretty clear at this point that we are witnessing the dawn of the era of precision physics with gravitational waves. So, but the point that I want to focus today is basically that I believe that symmetries at the theoretical level can really help us shed light on the fundamental aspects of gravity and black holes in particular, and also constrain broad classes of theories beyond general relativity in a model-independent way. So something that sometimes I also I'm a bit surprised about that. So black hole perturbation theory has really a long history. That started with the works by Reggie Wheeler and Zerilli. But interestingly, as I will show you, there are recent results that suggest that there are some deaths, in fact, that are yet to be planned in this field. And I will focus on two observables. The first one is the black hole, the love number, so the tidal deformability of a compact object. And the second is quasinormal modes. And I will organize the presentation, if you want, in 3 sections. The first one, I will mention some recently discovered symmetries of black holes, which we call ladder symmetries, and the relation with the vanishing of the love numbers. The second is, I will tell you more about symmetries and dualities for black holes. And third, I will mention something about an effective field theory approach to study the ringdown. Okay, let me start from the first one. Again, I don't want to spend time on the introduction, but let me just mention that we all know that there is one important property of black hole perturbations, which is called asymptotically. So the fact that the even and odd equations that describe the black hole perturbations have the same characteristic frequencies, the same spectra of quasi-normal modes. And this is called asymptotically. What I want to emphasize is that this property has been known since the 70s. So it's something. So the fundamental origin, if you want, the symmetry which is responsible for this property has been known since the 70s, thanks to a work by Chandrasekhar. And but on the other hand, there are other aspects about black hole, like the vanishing of the lab numbers that was unclear until last year, basically. So this is something that I mentioned yesterday. So I guess we all know it, but let me just say it again very briefly, just to define to be so that everybody's on the same page. So let me consider the example of which I like, of a dielectric sphere in electromagnetism. We know to compute the induced polarization if we put this dielectric sphere in an external electric field, right? We solve the Laplace equation outside and inside. We impose some matching condition across the surface, and we compute the response coefficient, the L of the induced in the potential. So if we do this exercise for L equal to 1, this is the result. But in principle, we can do everything for generic L. So this is a simple exercise for students that take a course in electromagnetism. So instead, if we consider a black hole, instead of the electric field, we consider a gravitational tidal field. This is basically the same exercise. And these KL are the lab numbers, as you know. And of course, if we consider a generic object like a star, a neutron star, we know that these coefficients are non-zero. And there is in principle no reason why they should be zero. But this is what we observe, what we measure, it is the result of a calculation in GR is that these coefficients are basically zero for the black hole. And again, this is something that is observationally particularly relevant, because whether or not an object can be deformed, tidally deformable, affects, of course, the signal, the gravitational-wave signal. So this is something that is really important to keep in mind, and is in fact an important channel to test the general relativity and compact objects in the strong field regime. Okay, again, I'm not spending time on this introductory part, so, but please interrupt me if I'm going too fast. I don't think so, but I don't think there is any need for an introduction to this audience. So let me go right away to the point that I want to make, which is the following. So a conceptually clean, if you want, way to define the lab numbers is in terms of a word line effective action. The idea is the following. If you look at the black hole very far away, the black hole is basically like a point particle. And we can construct an effective theory that describes the properties of this point particle object. In particular, corrections due to the finite size of the object are taken into account in terms of irrelevant operators in some effective field theory sense. So basically, this is the action, this is the word line action, the point particle action of this black hole very far away. We have the word line part, which is basically the word line of this particle, and then we have derivative operators. Like in any standard effective field theory, we have derivative operators that take into account the fact that actually this object is not a point. And in this framework, which is the effective field theory, the lab numbers are basically the coefficients of these relevant operators. In principle, you can add also a couple. This G coupling would be the analog of the hair for the black hole. Okay, so this is very nice. This is very beautiful. This is very general. Actually, this works for any object, not only a black hole. So if you want to describe any compact object far away, this is the correct framework. Okay, and there are two properties that you expect to be true for this effective theory, but in general for any effective theory. The first one is that these couplings in units of, let's say, the radius of the object are expected to be order 1 numbers, so order 1 couplings. Second property is that we generically expect to have some, in this case, classical RG running. Okay, so and this is what happens for again a generic object. But if you consider the black hole, neither these are order 1. In fact, these are 0, and 2, there is no RG running. So this is the reason why the vanishing of the love number is kind of a puzzle. Notice in particular that, which I think you already know, but let me mention that this is true only, so this is true in 4 dimensions. If you consider a black hole in arbitrary dimensions, these love numbers can be non-zero and there can be an RG running. So it's a very special property of 4 dimensions. Yeah.
So, I'm afraid a very silly question. What is RG running?
Well, like that, there is a dependence on the scale, like in any standard effective field theory. You expect some running in the couplings, and this is true in general dimensions. If you compute the love numbers in higher dimensions, there are cases in which basically the love number depends on the scale where you measure it. So there is some logarithmic running of the love numbers.
Okay.
But thanks for the question. So please ask questions. Otherwise, I will, again, I don't have many slides, so I will finish very soon. Okay.
Why does this happen?
Why are they 0 in D equals 4? Well, exactly. This is the result of an explicit calculation. Of course, in this effective theory, the effective theory does not tell you that these are 0. The point is that I give you the effective theory. On the other hand, I give you GR. We know to do calculations in GR. You do the same exercise of the dielectric sphere, now with a black hole, and you find that the love numbers are 0. You do the matching between the EFT and the UV theory, which is a standard procedure for effective theory, and you discover that these lambda L are basically 0 because in the UV the love numbers are 0.
So it's something that's imposed on the EFT because you know that result from a linear calculation of GR.
After you do the matching, exactly. Just after you do the matching, lambda L are 0 because the UV theory they are 0. Like in any, well, like for I would say in any effective theory, we can integrate out some UV physics. We can work with some very general effective field theory. Of course, once you have the EFT, you can, depending on the UV model, you can do the matching and discover what are the couplings in the EFT. In this case, if you match the EFT to this UV theory, you discover that lambda L are 0 because in the UV the result gives you 0 love numbers.
So if you didn't know how to do the calculation in the UV already, like explicitly, you wouldn't know how to do the matching, and then you wouldn't get this result.
Yeah, let me say in a different way. Suppose that instead of GR, you like a different theory of gravity, maybe in which love numbers have there are the love numbers take different values. Of course, you do the matching with this different theory of gravity, and you discover that lambda L are different now.
Just before you start with this sphere example, you said that in the gravitational-wave, the field is the gravitational-wave. Here actually, the scalar field that's played.
Perfect. Yeah. Thank you for the question. Exactly. Yeah, I didn't say that, but for simplicity, here I'm considering a scalar perturbation, so a black hole inside some scalar perturbation, but this can be generalized to spin 1 and spin 2, so really to gravitational perturbation. So a black hole inside a gravitational perturbation. perturbation, gravitational tidal field. That's correct.
The fact is, from what I know in cosmology, you like that the long wavelength smooth, you can just gauge them away by gauging the direction. So it's not the same way with the one.
Yeah, you're talking about adiabatic modes, I guess, in cosmology. That's an interesting question. So it's this is something that, yeah, that's a very interesting question. I don't think people, well, I'm sure that people didn't figure out what is the analog of an adiabatic mode for black holes. But I think that there are evidences that there are no. It's a little bit tricky to draw the analogy. So in this case, I'm really talking about a physical tidal field, not something that you can gauge away like an adiabatic mode in cosmology. The questions, but thanks. Yeah, it was very good question. Okay. So, and so it has been known since a few years that the vanishing of the lab numbers is a puzzle for what I said from the point of view of an effective field theory. And this, of course, looks like something that can be very likely explained in terms of symmetry in the theory. And this is what I will be telling you. In fact, in this work, we show that the vanishing of the lab numbers is a consequence of linearly realized symmetries that govern static perturbations around black holes. And the same symmetries are connected to well-known no-Kerr theorems for black holes in GR. So let me summarize what are these symmetries. So underlying these symmetries is, if you want, a ladder structure that can be used to construct a full tower of solutions and derive two main properties. The first one is that solutions that decay with the radius far away spontaneously break the symmetry and must be divergent at the horizon. Instead, solutions that are regular at the horizon respect the symmetry and take the form of a finite polynomial. So property one is basically consistent with no-Kerr, so it's basically the no-Kerr theorem. 1 and 2 combined together imply that the lab numbers are 0. Okay, this is what I will be showing you now. Okay, so this slide is pretty dense, but let me guide you through the slide. So let's consider again the case of a scalar field. But as I said, in principle, I will mention this later. This can be generalized to higher spins, in particular spin 1 and spin 2. And so let me start with the Klein-Gordon action, in which I take a decomposing spherical harmonics and zero frequency. We are interested in static perturbations. And let me define this delta, this combination here for simplicity. And the equation of motion, the Klein-Gordon equation is Schwarzschild spacetime, now can be written in this compact form here and we can define this as a sort of Hamiltonian, okay? Now you can do the following. Define these two operators that I define with the plus and the minus. And these operators is just algebra, satisfy this sort of commutation relation. And in particular, you can rewrite this Hamiltonian in terms of this the plus and the minus in this way. So this is just algebra, nothing more than that. And it's a property of these operators that they commute in some sense with the Hamiltonian in this way. Okay, so if you take, you act with is HL, and then you act with the plus. It's like acting first with the plus and then H at level L plus 1. Okay. L is the quantum number in the spherical harmonic decomposition, of course. So the claim is the following. So far is algebra. The claim is the following. These D plus minus are basically ladder operators in the sense that if you start with a solution at level L, which satisfies the equation of motion, and you act on phi L with d plus minus here, you automatically construct a solution at level L plus minus. In this sense, they are a ladder operator. So if you have a solution, you act with this plus minus, you automatically reconstruct the whole tower of solutions. Okay? And let's consider an example. For instance, if we take, let's look at the Hamiltonian HL again. For L equals 0, it's pretty clear that phi 0 is equal constant is a good solution. Okay? Now imagine that I want to construct all the other solutions, just a matter of adding with the d plus operator until up to the L level. And basically what I find is a pure polynomial in R, which is, you can check an exact solution of the original equation. There are two properties that this solution has. One is that it is regular at the horizon, of course, and two, that it matches the tidal field boundary condition far away. Okay? Perfect. Okay, very nice. Now, let me add another piece of ingredient. Let me define another object, which is this QL operator here, defined recursively in this way using this plus minus operator. And actually, you can check that this QL basically commutes with the Hamiltonian. So in this sense, it is conserved in some sense. And you can check that this is a symmetry. This object, for this reason, generates a symmetry of your original equation of motion and of the, or if you prefer, of the scalar action, the action of this scalar field on Schwarzschild. Okay? So since it is a symmetry, you can compute the nether charges using the standard procedure. And this is basically the nether charge, which is conserved. Okay? Why is it useful? First, we call this horizontal symmetry as opposed to contrast with this ladder symmetry, okay? Because this QL acts only at level L. But let me tell you why is this interesting. Well, because using this charge, you can automatically, connect different behaviors at the different singular points, at the different boundaries. In the following sense, imagine that I start with a solution, let's consider here with L equals 0, the solution that very far away, we know what are the two possible profiles far away from the black hole, right? There is R to the L and R to the minus L plus 1, okay? But let's consider this one, that it became with L equals 0, so 1 over R, okay? Now let's compute this PL, 1 over R. If you use PL with L equal 0, you find that it's non-zero. It's a constant, and it is non-zero. Now this is enough to know what is the profile of this solution close to the black hole. The only possibility for this PL to be a non-zero constant is to have phi L going like a log. So there is no way this solution can be connected to a solution that is regular at the horizon. So a solution that has a decaying profile is always divergent at the horizon. Notice that here I never solved explicitly the differential equation. So I never said, you have never seen an hypergeometric function here. Okay, so this is only based on symmetries. Okay. Second point, and now let's do the same exercise with, let's consider L equals 0 again. So the constant solution, let's consider the solution that has a constant profile far away, which matches the tidal field boundary condition. Now let's do the same exercise. Let's compute the PL. PL is 0, and the only possibility to have PL equals 0 close to the horizon is again phi L equal constant. In fact, the constant is a good solution everywhere. Okay? Perfect. but this is true for any L. So, yeah.
When you say at the horizon, at the bifurcation point.
I mean at RS. I mean at the point where this delta vanishes. The Schwarzschild radius.
But at which time you're using Schwarzschild?
Well, here everything is there is no time actually because I'm considering static perturbations. I'm taking just take the Klein-Gordon equation on the Schwarzschild metric, which is the line element is basically 1 minus Rs over R dt squared plus dr squared over 1 minus Rs over R.
I'm asking because I know that if you look at quasinormal modes in Schwarzschild, then they're not both to as you go towards the bifurcation. But if you take horizon slices, they're more opaque actually. At future horizon are opaque. So I wonder if this is caused by going through the bifurcation point, or if it's caused by, or if it's like if it would be there also, if it would be true at the future horizon.
Well, here it's hard to say because again, this is everything is static here.
Yeah, so I don't see that.
Yeah. Okay. Yeah. Thanks for the question. Other questions? So let me summarize. So the vanishing of the lab numbers basically follows from two facts: that the purely decaying solution is divergent at the horizon, and the solution that is regular at the horizon is basically a finite polynomial. So there is no 1 over R tail, and the going branch respects the symmetry. So in this sense, it is linearly realized, and the decaying branch spontaneously breaks the symmetry. So it's non-linearly realized in this sense. So fact 1 is consistent with the no-have theorem, as you know, and so the fact that a black hole cannot have a static scalar profile that decays infinity. Okay. Okay. Yeah, let me mention something else, which is kind of nice. So the symmetry actually has a geometric origin. So in fact, it is related to the isometry of an Euclidean ADS space in the following sense. Consider the scalar action in the static limit again, which is this one. And this scalar field, this static scalar field lives on this effective metric. So basically, if you take the equation of motion associated with this action, with this metric, it's basically, and you compute the equation of motion, is basically the Klein-Gordon equation in the static limit, okay? Now, consider a Weyl rescaling. So you do a Weyl rescaling in the metric, and you rescale also the scalar field. With this, there is a constant divided by the delta that I defined before. So again, some algebra, and you find that the action takes this form, and now the metric is this one. So it's basically Euclidean ADS 3. And this Euclidean ADS 3 has 6 kilivectors, 3 rotations and 3 translations or boosts. And the translation that mixes the radial coordinate that here is a star, which is related to R in this way, and the angles theta acts on the scalar field in this way. So just to say that this is a symmetry, well, I'm using all these analogies with the ADS, but just to say that the point that I want to make is that this is a symmetry of this action. I'm just saying that, okay? And I'm saying that this can be reinterpreted in terms of a killing, an isometry of some Euclidean ADS space. The nice point is the following: if you take this symmetry and you go to you do a spherical harmonic decomposition, you discover that this is in terms of spherical harmonics in L space is basically the superposition of the ladder operators that I have before. These C are just coefficients that are L dependent, so they're not very important. The important point is that this isometry is is basically related to the ladder operator. So the ladder operators are basically related to the isometry of this ADS 3 space. Yeah.
I may ask a question. In this rescaling, bar rescaling, so you're rescaling the amplitude of the scalar field by omega to the -1/2.
Yeah.
How do you determine like the exponent of the omega? So I'm asking because I'm used to conformal rescalings where you rescale it by just omega to -1. So I was wondering where the differences lie.
Well, it's just yeah, it's the power in such a way to have an action which has the standard, let's say, kinetic term.
Okay.
You need something that cancels exactly. Otherwise, you will have a field which is not canonically normalized.
Okay.
Questions? Okay, so one might ask the following question. So what happens if I take the large distance limit? So if I consider this symmetry and go very far away, r that goes to infinity, well, there is a non, the symmetry is not trivial, nothing bad happens actually. And in fact, this symmetry reduces the special conformal transformations flat space-time, flat space. And we claim that this is basically the infrared symmetry that forbids lab number couplings in the point particle EFT. A special conformal transformation, which is basically what I've written there. Okay, yeah, let me mention the following. So in binary systems, the induced deformation is never exactly static. So the question is it possible to extend these ladder symmetries at finite frequency? Well, the answer is yes, in the following sense. And this is something that we finished a couple of weeks ago. So let me consider the action of a scalar field. Again, I'm doing everything for a scalar field, but I will mention how to extend to higher speeds. Let's consider the action of a scalar field, which is this one. And let me define some near zone approximation. Let me replace basically this factor with this R with an RS. Of course, this is an approximation, which is becomes correct if you go very close to the black hole, which it's not correct, of course, if you are far away, but it still captures quite well the dynamics as long as omega r is much smaller than 1. Already?
More or less.
Wow, fantastic. I thought I was very fast, but I'm very slow apparently. Okay, anyway, I'll finish when I finish. I'm happy to chat more if there are questions. Okay, sorry, yes. If omega r is much smaller than 1, and in this limit, basically you can show that the scalar action is the same of the action of a massless scalar field minimally coupled to an effective metric, which is this one, which is a near zone metric. And this metric has two main properties. The first one is that it's the only extension of the dynamics of finite omega that retains the ladder symmetries that I told you before. And two is a conformally flat ADS2 cross S2 geometry. So this means that it has 6 Killing vectors and 9 conformal Killing vectors. Let me be more precise, more specific about this. So these are just symmetries of the previous metric. These are the 6 Killing vectors, and these are the 9 conformal Killing vectors. Let me not enter into the details, but let me stress some crucial, some key properties of these objects. First, so one of the reasons why we wrote this work is to clarify an aspect which was kind of confusing before before, the fact that I've been telling you this the story about the ladder symmetry. There was another paper by Sergei Dubovsky and others that proposed a solution to the problem of the vanishing of the lab numbers working at finite frequency. So we wanted to clarify what is the connection between our work, our ladder symmetries, and this work. And the reason is basically the following, that these ladder symmetries and the symmetry discussed here are basically, at least in the Schwarzschild limit, there are some differences that I'm happy to tell you about for a rotating black hole. Is that these symmetries are basically part of a larger picture, which is basically the following. And in particular, these T and L plus minus are basically the symmetries discussed here. J01 is basically the ladder symmetries that I've been telling. But notice, let me stress that only T, Jij, and J0i, so this one, are good symmetries in the static limit. The others are not good symmetries. In fact, I didn't tell you about the other operators before, because they have some time dependence here, okay? You can interpret these operators in like some ladder in omega. They generate solutions at finite omega, which in principle brings you out outside the regime of validity of the approximation. Okay, but yeah, just to mention that this J01 is basically the ladder symmetry that I told you before. And notice that the ladder generators are useful because they allow to divide some conserved charges for each L. And in particular, if you compute these charges, you can find this quantity here, which reproduces nicely the induced multiples that have been computed explicitly in an explicit calculation, basically. Okay, maybe I can skip this. So this is just to say that you can extend everything to Kerr. Basically, what I told you before can be generalized to a rotating black hole. So you can find the ladder symmetries for a rotating black hole. And you can extend also the story at finite frequency for a rotating black hole. You still have a ADS2 crosses symmetric, so you have 6 Killing vectors and 9 conformal Killing vectors. But let me maybe mention the following. Let me see. Let me mention the following, which is probably something that connects to. Okay, let me say tell you the following. So this is the. Let me mention what happens for higher spins. This is the Teokolsky equation for a generic spin S. You can find ladder operators that brings you from S equals 0 to S equals 1 and S equals 2, basically. There exist also ladder operators in this sense, ladder in spin, which we call ES plus minus here. Let me make the following connection. It's these ladder and spin operator are nicely connected to the so-called Teokolsky-Starobinsky identities, which you might know, which are the following. If you check Chandrasekhar's book, Chandrasekhar writes that basically phi S with S equals -1 can be obtained adding with some operators on phi S equals to 1, right? And the same for between -2 and 2. But you cannot jump between consecutive spins, right? The new twist that we are adding here is that in the static limit, actually you can truncate these Teokolsky-Starobinsky identities. And basically, the truncation, these operators become these plus minus. So there is a connection between this ladder spin and the Tucholsky-Starobinsky identities. Apparently, this was not, I don't know, noticed before, because of course, in some sense, the Tucholsky-Starobinsky identities are more powerful because they hold for generic frequency. But people, I don't think that they realize that if you go to the static limit, actually, you can do better in the sense that you can stop at intermediate levels. Okay, I think this is a nice property that at least I was not aware of before. Okay, maybe I'm out of time.
So I'll take 5 more minutes, maybe a bit more.
Well, yeah, it's incredible that I thought I was finishing before, but I'm behind. But okay, I'm happy to discuss. I'm happy to stop here to discuss something else. So again, I was hoping to something more informal. So maybe.
I mean, in total, we still got 15 minutes. So, I mean, if there's questions, we can start with questions. Otherwise, if you want to keep on going, I don't know what.
Or I can tell you something very briefly about effective field theories, or you tell me. Yeah. Yeah. Yeah.
And it's also zero.
Well, it's zero the conservative part. There is a dissipative response that is non-zero. So the conservative response, which does not break time reversal, if you want, is always zero, both in Schwarzschild and Kerr. Zero frequency, finite frequency. If you consider a rotating black hole at zero frequency, so zero frequency perturbations, or a Schwarzschild black hole but non-zero frequency perturbation, you find a dissipative response, which is non-zero. Yeah. Yeah, it's a matter of terminology. They meant that there is a non-zero response, but that response, so usually, maybe it's a matter of taste. I would call that number the conservative response, which is still zero. They meant they were referring to the dissipative response, which in fact is non-zero. Dissipative, I mean that it's imaginary. In fact, there is an I. I mean, what they do is correct. They find the correct result. It's just a matter of definition. Are the ones?
The ones in columns above, like you have asymptotic behavior that are one over just over.
Yeah. The profile is, maybe I can show you. Yeah, the profile is the same, is that the coefficient is imaginary. So you can think of it as breaking time reversal. So in this sense, it's dissipative.
So what happened in the H-symmetries? Alpha on my two alpha on my.
So you consider the extremal limit?
Yeah.
That's a good question. So in the extremal limit, let me think. So you're talking about the static limit. Let's see.
Your formation color
yeah, I think that you have to be careful here. Yeah, in principle, nothing bad happens in the metric, in the Tucholsky equation, in the extremal limit. I'm a little bit confused now about the Q that is there, but yeah, that's a good question. But there is a Okay, I have to think about. So I'm pretty sure that nothing bad happens, but now I don't see it. So okay, let me think, and then we can I can tell you. Yeah.
So one question. So there's like a relation between these larger symmetric K vectors and conformal vectors. Right?
Yeah.
So in the Kerr case, those K vectors have any relation because I immediately think of the Carter constant and T vector.
Yeah.
Do they have a relation with these larger symmetries?
Yeah, that's a good question. Yeah, I think we have to be careful because, of course, when people talk about the killing tensor, and symmetries of Kerr, these are symmetries of the Kerr geometry. Okay, here I'm talking about isometries and conformal killing vectors of an effective metric. So like this one. So this is not related to Schwarzschild. This is not, for instance, any near horizon limit of the Schwarzschild metric. This is just an effective metric that gives you the correct equation of motion. So this is completely separate from. But that's a good question. There could be some connection between. Well, that would be very interesting if there is any connection between, in the Kerr case, between these asymmetries and the killing tensor. That would be very interesting, but I don't know. I didn't think about that. Yeah.
There is some dualities that are known.
Well, so these asymmetries, this S2 cross S2 has been studied for a long time. I guess this is what you're referring to. Works by.
For example, when this is I wanted to know if you can have more information on this.
Yeah, that's a good question. Not, I don't know at the moment. I don't know. Yeah, that's a very good question. I don't know if you can. Well, yeah. Yeah, I didn't think more about. I didn't think much about this, but that's a good question.
Because it's a bit weird because this is an approximate. Some
well, notice that. Well, let me stress that so this near zone, of course, has been known as we are not inventing it. So this has been known since the works by Starobinsky, Maldacena, Strominger, so on. We are just highlighting the fact that some of the isometries of this effective metric, which comes from the near zone approximation, are related to these ladder operators, which have a consequence for a gravitational wave observable. So this is the point that we want to make. But these symmetries, these ideas, 2 cross 2 has been known for a long time.
So in the Kerr case, we also you're always in the scalar action, right? Yeah, because I was trying to do and they have all of these mixing between different very complicated things. So in your case, you cannot see that because it's scalar.
Sorry, but let me understand what you are referring to. Is it so? Which kind of is it Kerr? Do you have a
so I think right here with that, so there's basically that scalar perturbation is good to sort of link the deformability of the body, but there's also another type of like current deformables that are on the axial part, and there's the same thing for the tidal, right?
But you're not referring to, you're not talking about the Tchaikovsky equation for S equal to, are you?
No. I'm just talking about symmetries in general right now. Because we have all these two types of symmetries for the electric and the magnetic. And there's also, when it's rotating, there's a can be coupled. So I was wondering if yours are to be the
Well,
scalar.
yeah, that's a good. So what we do for a spin 2 basically is a little bit indirect in the sense that where is it? So just a second. So we, if you want, we infer the properties for spin 1 and spin 2 using this Ladder mass. It would be interesting to see if one can work, I don't know, directly for spin 2, maybe, well, I think the best, what we can do is, the best we can do is at the level of the Tchaikovsky equation. We don't have an action. So, well, so, I mean, the short answer to your question is that I don't know, but that's,
So this was the slowly spinning the approximation, right? That is the completion of the and calculating those numbers that would be used by the reality tidal field by telling the speech that it is.
Okay, yeah, you can show me, you can remind me the paper, and then we can discuss. I can
comment on that. I think a difference is that so they are doing a spherical harmonic decomposition, so it's not exactly the same L that appears in this equation, right? Because it relates to spheroidal harmonics.
Well, yeah, so the static limit, yeah, it is true, but it's in the static limit, so you can, yeah.
But even for S different than here, it's not the same. So you get spin weighted.
That's right. Yeah, I guess so. Even though, so the eigenvalues are basically these, right? Right. So
Which are the same as spherical harmonic.
Yeah.
Yes.
Okay, but it would be interesting to check it. Yeah, okay.
More questions? So then, maybe if I can ask a question too. It's actually, well, maybe more related to, well, something that we also mentioned yesterday at the colloquium, because everything here, I mean, you're showing is at the analytical level. Have you done, are there any numerics that you can do related to any of the topics you've covered, or?
Well, not related to this one. Something that I didn't mention is about more related more to effective field theories and these kind of things, where again we did so far only the analytic part. It wanted to be interesting to see if there is a way to connect to more numerical stuff and more to the data if you want. So yeah, that would be very interesting. Yeah.
So, well, I mean, we got 3 more minutes. If there's any other questions, we can have more questions. If not, if you're happy, we can also leave it here. So 1, 2, 3. So then let's thank our speaker.
If you enjoyed the video, like and subscribe.